Hey, can you hear me? Yes, okay, that's this one. So can we start?
Yeah, and as always, it will be more a conversation than
Yeah.
a talk. Be ready to be interrupted.
Yeah. I mean, I made a presentation in a way that it has like questions that are printed out there. They're in the middle, so we'll stop for discussions. Unfortunately, they're not in the same order, but still.
Go ahead.
Okay. Hello, everybody, and welcome to the discussion on intermediate mass black holes. I'm Igor Chilingarian, and I'm an astronomer here at the CFA. And this will present first some of the results that were obtained in the framework of our little collaboration that includes mostly Russian expats who are now all over the world, almost everywhere except Russia, for the reasons you might guess. And also we have like representation from Chile, including Professor Bauer, who is actually originally from Ann Arbor, Michigan, who's a full professor at Colloquium, and his student Ernesto Camacho, whose name is underlined here, and I underline his name because he will come here as a pre-doc, actually starting next week for a year. So he'll be working mostly on the variability of intermediate mass black holes. So before we get into science, first an announcement. We are trying to recruit students to collaborate and work with us on the IMBH. So some advertisement slides. You know, we are not always nice to our students. We keep them on a leash, as you can see here in this picture. Like, make them fight off scary animals and, you know, get their own food from the trees because we don't feed them. So they have to learn the survival skills, and then we put them through survival experiments at high altitudes. You know, the observers have to get adjusted to the altitude, so you have to know what to do. So we do this. It's not always going really well, but so far the survival rate is 100%. And at the end, we make them do our own work, of course. You know, do you think I really want to refill the nitrogen? Of course, no. But okay, they also know how to write proposals, generally in our team, so we'll teach you this too. So if anyone is interested, undergraduate, graduate level, it's observational studies of intermediate mass black holes. I have resources here, like funding sitting in the CFA, so we can support students. And if you're interested, just come talk to me, or if you know somebody who would be interested. Okay, let's go to the scientific introduction. The ultimate goal, the ultimate question we're trying to answer are, what are the supermassive black hole seeds and how did they grow into supermassive black holes? And interestingly, these are the questions that were highlighted in the most recent Astro 2020 Decadal Survey as key questions for astrophysics for the next decade. And we're trying to find an answer, to look for answer and find it by studying a population of intermediate mass black holes. So what is intermediate mass black hole? It's a black hole with a mass between 100 solar masses, which is considered like an informal limit for stellar remnants, for stellar mass black holes, and 100,000 solar masses, which is considered like an informal limit for the lowest supermassive black holes sitting in galaxy centers. And this is a plot from from a review paper by Marmis Kua, and she probably should start getting royalties for this plot because everybody uses it everywhere. So, which basically explains that if you start from low mass seeds, you will end up with leftover intermediate mass black holes. Whereas when you start from high mass seeds that are the results of direct collapse of gas clouds in the early universe, there will be no intermediate mass black holes because the seeds will already be generally more massive than what we see here. You will still have like a tail of the distribution, but there will be very few. And so I'm personally looking at all this stuff in the local universe, observationally, but the goal of this discussion is to discuss, is basically to extend this to theoretical perspective, to get some theoretical perspective, and also extend it to intermediate and high redshifts. So we searched for intermediate mass black holes in AGN, as low luminosity AGN using Sloan spectra, so basically did optical selection, and then tried to get spectroscopic follow-up and X-ray and so on. And in our first paper that was published back in 2018, we found 300 candidates selected from optical spectra from 1 million spectra of Sloan. Those were with virial black hole masses under 2 × 10⁵. 10 of them were confirmed in X-ray, and this grew to 30 plus at this moment. Most host galaxies resided in sparse environment, so low density, not in the clusters. And then we actually assembled an extended sample going up to 10⁶ solar masses to get connection with the SMBH distribution. And this already includes 2,000 objects with 140 plus detected in X-ray. I'll talk about it later. So what makes our search different from the others, like Green and Ho, and Rains and Green and Baldassari and stuff? We start from a full SDSS galaxy sample regardless of luminosity. So we don't have this dwarf galaxy bias, because we want to study scaling relations of black holes and their host galaxies in the low mass regime. It's kind of natural that if you start looking for stuff in dwarfs, and you'll eventually find low mass stuff in dwarfs, you'll get the scaling relations populated in the bottom left corner, and you might get a spurious relation even if it's not there, just because you were not looking for the outliers. So we also use non-parametric shape for emission lines, for narrow lines, that improves the sensitivity. But I will show it on the next slide later. And we use the homogeneous data coming from our database called RCSED, Reference Catalog of Galaxy SCDs. That's a little advertisement. You can get to the website and look at galaxies. We're now working on the second release that includes 7 million spectra from most available optical spectroscopic surveys. And we're now working on incorporating DESI that would increase it to like 8 million spectra for 5 million galaxies. So that's a slide that illustrates how we actually determine black hole mass. And that's like a cartoon representation of a center of a galaxy done by like a professional designer who we asked to help us with this slide. So you have a black hole with its accretion disk and corona around it. That actually emits a lot of high energy photons that ionize the ionize the gas around it. The inner part, the inner workings, which have the sizes of light hours to light days. This is a so-called broad-line region. It's an area with high density clouds, where the density is so high that, first of all, it's close to the black hole, so there's broadening because of Doppler, because of radial velocities of these clouds. And second, the densities are so high, so forbidden lines do not form there because of the density constraints. It's assumed that this part is virialized, which is actually a kind of strong assumption, but that's what we have to do in order to estimate the mass. So then if you go further, you have narrow line region, which is not virialized and which has lower density, where you already have forbidden lines, and these are the lines that I use to classify AGN on classical diagnostics like Baldwin-Terlevich-Phillips diagram, BPT. And this is all sitting in the very inner part of the galaxy. Typically for big AGN, it will be like a KPC size, and for IMBH powered AGN, it will be like 100 parsecs. So here you can see the optical spectrum with emission lines, narrow lines, and this is a zoom of the H alpha region. So you have H alpha and forbidden lines of nitrogen, which are narrow, and you also have this broad component that corresponds to the BLR. And from the flux and shape of this component, we actually infer the mass. The idea here is simple. If the luminosity is high, then the size of the broadline region is larger, so then this line actually becomes narrower. It becomes brighter but narrower for the observations. But on the other hand, like the line doesn't get narrow by itself, but the outer part becomes the inner part corresponding to low velocities become brighter, and so you might end up measuring lower full width maximum. And so if the black hole is more massive, then the line is broadened. Then if the Eddington rate is lower, so then you're seeing only the inner parts which are broadened strongly. So here's the main question, number one. Can we and should we trust single epoch virial black hole mass estimates? So why the question is important? Because this is like a tertiary mass estimate. This is based on the extrapolation of the so-called radius luminosity relation for broadline region to the low mass regime. The radius luminosity relation is established by measuring sizes using reverberation in much more massive black holes, where you can get the black hole mass estimate using different means like stellar dynamics, which are considered independent of this. Stellar dynamics or gas dynamics using like CO observations with ALMA and things like this. So whether this extrapolation to low luminosity is actually accurate, we don't know. The assumption about the geometry is crucial here, and if you go from disk to spherical geometry, the mass estimate will change. So generally we're talking about 0.3, 0.4 dex precision for this, so a factor of 2 to 3 in terms of statistical uncertainty. But this might be underestimated. Yeah?
So, Igor, I've always been confused about this radius luminosity relation. I know it works. Now, the thing that has confused me is I expect the relation to depend on how much gas is present around the black hole in this nuclear region, but the relation doesn't seem to care about that. It says it's all same for all supermassive black holes. Why?
That's what I don't know.
Okay.
Like that's. I mean, I also look at this radius luminosity relation as like an empirical thing that is found by observers, and it's studied pretty well down to the masses of 5 times to the 10 to the 5, and it indeed doesn't depend on the amount of gas. But how can we actually estimate the amount of gas? That's another story.
I assume that it's going to be all over the map for different systems.
Now, in fact, it's not.
It's not. Okay.
It's not, because the correlation is pretty strong. Yeah. I think that if I remember correctly, the RMS is like 0.15 dex for the RL relation that goes to 10 to the 6, 5 times 10 to the 5 solar masses. How it behaves at low masses, we don't know. Yeah. So what are the pros of the virial mass estimates? They're super easy to make. So you just have to get your spectral analysis straight. So if you can recover the broad lines and you think that these broad lines come from the AGN and not from like a nuclear rapidly rotating star forming disk or something like this, which also can happen in massive galaxies, that's very easy and very cheap. And you can run it against millions of spectra and infer mass estimates from actually everywhere where you see broad lines. Of course, there's extinction, and extinction can play a role, but the dependence on flux, it's actually quite small. It's square root. So if you don't, unless you make a really big mistake about the extinction, it should matter. So what are the cons? We don't know the virial factor, so basically we don't know the geometry. So the extrapolation is uncertain. Now the question is, what are the alternatives? And I listed here like a couple of possibilities. One of them is so-called normalized excess variance. It's the rapid X-ray variability studied well, basically, if you observe an AGN for a sufficiently long time in X-ray, you can build the power spectrum of the variability of your light curve and estimate there should be some stochastic variability. And it is claimed that the degree of this variability is actually higher for low mass black holes. So there's a correlation that goes, again, everything stops at 10 to the 6. There was a paper by Ludlam 2015, and then there was a theoretical interpretation by Pan et al. 2015. And they were claiming that the relation should saturate in the IMBH regime, which is bad news for us. Whether it indeed saturates, we don't know, because so far the only AGN which is powered by a relatively low mass black hole, where you have enough X-ray photons to study this stuff sufficient detail, is NGC 4395, just one galaxy. Well, I think we found another one that is also nearby and that also has like an IMBH inside, but it's still like a factor of 3 more distant than NGC 4395. So we don't know what happens to the normalized excess variance in the low mass. Another way is to look at the QPOs, because they're supposed to be related to the inner accretion disk radius. However, again, what's happening in the low mass range is unknown. So anybody here, can anybody offer any other alternatives?
I mean, I wouldn't trust the QPOs. In theory, what you say is right. But at least, you know that for X-ray binaries and variability of X-ray binaries, Chris Don has established that could depend on the quantization radius, not the gravitational radius of the disk.
People claim that there is a correlation for supermassive black holes, but yeah. Alexei?
So why does frequency not depend on the mass and the radius?
It actually depends. It depends on both, though. That's not correct what is written, but the major thing is the radius would be like the characteristic time scale depends on the radius. It's mass over area. Yeah.
But it depends on both.
It depends on both.
Depends on both, but
the radius could depend on the structure of the accretion disk. Yes.
But the underlying
So it's
assumption
like,
is,
sorry.
for a given mass, this characteristic radius is always fixed at something, innermost stable circular orbit or whatever, that they are tied together.
Mm-hmm.
And as Pepe says, that is the underlying assumption,
at
and
least
who
in
knows if it's true.
in some sources it's been demonstrated that
It is not. Okay.
Sorry, maybe it's trivial, but I thought like ISCO rotation time period, it's proportional to mass or something.
Mass over
The
radius.
point is that, that's correct.
Okay.
But what you see in these QPOs anyway is not the ISCO.
Okay.
It's the fact that the inner radius of the disk doesn't depend just on gravity, but depends on the structure of the disk. So,
Yeah, I would say that if you look at the papers describing QPOs, they would say, okay, we take 10 RG. Why 10? Well, because.
By the way, another method is probably if you have TDEs, the tidal disruption events, you can, in principle, infer the mass of the black hole.
In principle, yes, but those are rare
Those are rare.
compared to like.
I mean,
But even though, yes, this I've always heard this claim that TDEs happen more efficiently around intermediate mass black holes. Well, we can imagine why, because the gradient of the gravitational field is higher. But where the black hole have any black hole masses been measured from TDEs? That's a question to TDE people. Yeah.
Maybe one or two, but it's all everything is generally the spin, which you don't know. So you're fitting nigration viscosity with like a bunch of photons from the BN tail, so everything is degenerate.
Okay.
I mean, I would say that they're being measured
Yeah.
in a model-dependent way, right?
Yes.
And it's like, we don't know if that's truth, but like you're applying a model and you're saying this is the mass that comes out the other end of that model. I don't think it's totally prescriptively any different than the exercise that we're talking about here, where you have some model and you're applying it and it's giving you back your mass. So I do feel like those are parallel. We don't know how they compare to like a real ground truth of the mass of a particular source.
in that case, I mean, there are different methods, right?
Yeah.
If one could have a few objects in which you do both measurements and
Mhm.
compare, that will calibrate.
Yeah, and it's interesting, so there are tidal disruption events where they see a QPO, that sort of thing.
Yeah.
That's like work by Durage.
Okay. Yeah.
Depends how well you want to know the mass.
How well? Yeah, I mean, you know, sometimes you read papers and they claim, oh yes, we have the black hole mass of, I don't know, 10 to the 5. And then you start reading and you realize that they actually take the extrapolation of the M sigma relation and they say, okay, it must be 10 to the 5. No, that's not what we're trying to do here.
For these small galaxies, you can use the stellar mass, the M sigma, the fit of the extra spectrum. They all tell you it's in the ballpark or 10 to the 5 to the 6, which is good enough for a starting point. But if you want to use it as a
Yeah,
as an
if you want to
estimate,
build a scalar relation, you cannot use the very same scalar relation to determine the mass. That's kind of the main point. Because I often give talks about IMBH at conferences that are not exactly on AGN, and then people say, how did you determine the mass? Did you use M sigma? I say, no, I'm building M sigma here. I cannot use M sigma.
There is another way, which is, usually for very massive black holes, that the random walk of the black hole is very small, because the speed is square root of the mass of a star relative to the black hole times the characteristic speed of stars in the vicinity. But once you reduce the black hole mass, let's say 10 to the 4 solar masses, it's, the speeds would be 1%. So you would see the black hole moving around, wandering.
Yeah, so you mean the wandering black hole. Yeah, I was thinking
so
about
you
this.
can measure that relative to the center of the dynamical center of the galaxy.
Yeah, relative to the place where you think the dynamical center is.
Right.
But in Andromeda, for instance, the black hole is 10 to the 8, and it's offset. In M31, I mean,
Right.
and it's not offset. It's not offset because of the IMBH. So.
Right. No, but it's also an offset of velocity, not just position.
Oh yeah.
That's what
In
I see.
Andromeda, it's also like it's if you look at the inner part, there's an
Right.
eccentric disk
Right. Of stars.
of stars, and it's on the yeah.
Right. But in a spherical system, there shouldn't be.
Okay. All right. So let's go further. This is like an illustration of what we do in greater detail, and this is why we also need good data. So why we're not happy with SDSS. So this is a spectrum from MAGE at Magellan, where you see it's resolved along the slit, and so these are lines coming from narrow line region and star formation in the host galaxy, in this particular host galaxy. And if you zoom in on the H alpha region, you see this. So the broad line region is this big black thing that is point source in the sky. And this is the extended stuff that is broadened by Doppler motions, by rotation. And of course, if you take an SDSS fiber, you would incorporate, like a whole bunch of stuff here. And the lines, the narrow lines will already be broadened, which wouldn't affect the broad line measurement per se, but it would decrease the accuracy because you will be eating out parts of it. Anyway, this is the slide that I actually printed for everybody, and this is how different mechanisms of black hole and galaxy growth can move points around on scaling relations. So these are the two most widely used scaling relations, m sigma on the left and black hole mass, bulge mass on the right. And the one-to-one correlation is often interpreted as an evidence for black hole galaxy coevolution. However, we should keep in mind many different aspects related to this. And let's take a look at what we see here. Maybe, oh, I cannot really easily walk. Okay, let me try to do it here with the cursor. So there are several phenomena happening inside galaxies. So the black hole can grow, this one-to-one correlation assumes that bulges grow by mergers and black holes increase masses by coalescences during these mergers. However, it's not always the case. We have active galactic nuclei that grow by accretion, and accretion will push the black hole mass up, while it will not necessarily push the galaxy mass up, even though it could if you have large-scale accretion of gas that causes in situ star formation and secular growth of a thing called pseudobulge in the center of a galaxy. Then it can actually grow the galaxy bulge, the central concentration, by a lot, but there is no guarantee that this gas will actually find its way to the very center and feed the black hole. So in this case, you might end up with outliers in this plot that would be in the very high masses and also high velocity dispersions, but small black hole masses. And we do have such objects. I will show it in one of the next slides. Of course, when you look at m sigma, you should keep in mind that there is like a virial equilibrium that actually drives the things as well. And if your bulge is intrinsically more compact, then we'll have high velocity dispersion. So it will push it to the right on this plot, while it won't touch it here because it has nothing to do with the bulge mass. You can have the same mass but different size. So finally, you can have tidal stripping. And tidal stripping would leave velocity dispersion roughly the same, even though it would lower a little bit, but it can decrease the stellar mass by up to a factor of 100 for ultra-compact dwarf galaxies, or 10 or 20 for CEs, for compact ellipticals like M32.
Yeah, so you made the distinction between the two plots. Because compactness determines how sigma and m are related.
Yeah.
Which is the one that is tighter and that people think is fundamental?
People think that m sigma is tighter,
Okay.
which is actually, I don't know why, because from like general point of view, the one on the right should be tighter, but observationally it is not. So that's another like paradox, like why? But in fact, that's a very good point that you're raising, that the m sigma relation, as it is measured right now, it is tighter than relation with the bulge mass.
But keep in mind that there is the fundamental plane that relates the bulge to sigma. So plus another parameter. What do you mean? That's the fundamental
It relates bulge to sigma through size.
Yeah.
Yeah.
So that means that the scatter that you see,
No.
if you were to add the size, another dimension, they would be the same plot.
Like on the fundamental plane, you have the stellar mass, velocity dispersion, and size.
Yeah.
And in fact, the mass is like the mass is the primary parameter. Velocity dispersion and size, I would say, they are the ones that are related to make the same mass. But if you assume that there's coevolution, then the mass should drive the things.
All I'm saying is add another axis and the two plots will merge.
I haven't done this exercise, but I'm not sure that's the case.
Sure, because the fundamental plane tells you
Yeah, but fundamental plane assumes that the galaxy is sort of isolated and bulge is not like floating in vacuum. There is disk and some other parts of the galaxy around it. I think that this is more complex than this.
No, fundamental plane for early type galaxies.
For early type galaxies, yes.
Yeah.
But
so all I'm saying, try that.
Mhm.
Try that.
Uh,
You have data on
yeah, I mean,
branches.
that's right. I have the data. We looked at this at some point. We didn't find what we expected. That's what I have to tell you. Yeah. By the way, I have to mention one thing. There's one intermediate mass black hole now with the mass measurement that has nothing to do with all this stuff. It's a Maser estimate for IC 750. That's the only one at this moment. That's actually a compilation of data points taken from their paper from ZO plus 20. Okay, so why is it all important? Why are the growth mechanisms important for the observers? It's because this will tell you, like the one that dominates, will actually tell you whether the next space missions, the next generation space missions will see something. Because if early black holes grow predominantly by accretion, you expect to see a lot of active galactic nuclei, high redshifts, with new generations X-ray observatories like Athena and Lynx. I hope they will both fly. And then LISA will not see much because it's just not happening. And conversely, if the black hole growth is mostly due to mergers, even in the early universe, then we won't expect to see any AGN or many AGN. And then LISA will actually get the prize. So that's why it is important. Okay, now let me show a few slides about our own program. So we, after this paper in 2018, we started a big follow-up using all facilities we could get access to. So XMM-Newton, Chandra, Magellan, Keck, SALT, VLT, HST, JWST. So the idea was to feel the scaling relations and to look at host galaxies in particular. So what they are, whether they are what percentage are dwarfs, what environment they live in. Can we actually get some idea of what happened to them in the past in relation to their central black holes? Because, for instance, if you assume that this is an intermediate mass black hole that survived through the cosmic time without mergers, then you would expect it to happen in poor environment. Yeah.
So, can I follow up on what you were saying and be kind of, so I'm deliberately provoking you, but maybe other people can respond also. My kind of approach to some of these questions has been, well, we'll know for sure with LISA. Like, those are really accurate mass measurements. You see them across the universe. So, like, why would you not just wait and see?
Ask observers why are they pushing the limits with Keck telescope instead of just waiting for 10 years for JWST.
Yeah, I'm being deliberately provocative, but how will this augment or set you up for?
Because if LISA sees nothing, then what?
Well, then it already has been paid for, so I mean, let's push both frontiers.
Okay.
With LISA, you maybe will know. Sorry.
All these missions are always under threat of cancellation. So if you get an argument that's more refined about what it's going to see and make that prediction, it will help it continue.
But maybe it's a wrong argument.
Hmm?
Maybe the argument is wrong.
It doesn't matter for funding agencies.
But also, our lifetime is limited, and you want to have some answer before you die. So
That's it, it's death, that's all.
It all comes back to that. No, but I'm actually
Can you just
curious.
sit there and wait 20 years? Do you have tenure?
No, I mean, no, certainly. But I mean, there'll be astronomers then, presumably.
I think we should wait for faster than light.
Well, the argument will change if, for example, it says that the X-ray should not be funded. I'm sure you'll be against this argument.
Well, we'd be able to tell if this analysis.
So that's why it's important to launch LISA and links at the same time. So that the other one doesn't get cancelled because the first one sees something.
Anyway.
Okay.
So my, so with Lisa, I guess you know how many black holes there are in the galaxies, but you don't know how they accrete, which is also important.
Yeah.
But you know the occupation fraction, not the active fraction.
Yeah.
So in a way,
That's a
like,
great point. So you're learning one aspect of how they develop over cosmic time, but not the
but it's
other.
still interesting.
Yeah. So it's almost like you're learning one axis of this plot, but you want to know both.
Go ahead.
Yeah, also, I think this dichotomy, like light or heavy seas or accretion or merger growth is artificial. It's very likely that actually both are happening. And what's interesting is that, as Igor mentioned, those missions are mostly sensitive to only one aspect. So I saw projection, for example, on LISA rates, detection rates. And in the case of purely heavy seeds, there's almost nothing.
Yeah.
Okay, what it tells me is LISA is like not sensitive to the heavy seed population. And at the same time, a formation of a black hole through the heavy seed mechanism is one of the most, or maybe the most spectacular events in the universe. So you wanna see those, okay? So you wanna do statistics and you wanna see, something extra interesting, right?
Yeah.
And for those other, things you need, X-ray or
Also,
Yeah.
also I guess the LISA will give you an upper limit on net and the multi-wave
But
a lower limit.
to-
You
to-
observe a minority of the black holes in the galaxies electromagnetically, that gives you a lower limit.
Okay, so like if you see 1 in 100 has a luminous black hole.
It means it's at least one in 100.
Yes.
And LISA will not see maybe enough mergers, so it will give you an upper limit on the occupation fraction, and together they might actually give you a detection.
So we want to do both, and Igor, don't make a strong argument. We want to do both.
Yeah. I mean, I'm not making strong. You'll see my arguments later that we need both. Okay. So let me just zoom through the follow-up campaign. So these are the galaxies. These are SDSS images, I believe, or legacy survey actually. DESI legacy survey of the hosts that we observed with intermediate resolution spectroscopy with ESI at Keck, with RSS at SALT, and with MAGE and X-shooter targets. So we're getting to more or less 120 galaxies under the mass of 10 to the 6, with black holes under 10 to the 6. Most of them are X-ray confirmed. So we have our own HST snapshot program, and this is just showing, this slide just shows what we're doing with the data. We're trying to recover bulge masses, even though it's really tricky sometimes, because sometimes there's a bar, and then the question is, what is the bulge? Like, is it the little tiny compact thing in the center, or do you consider bar the bulge, or do you consider something else as the bulge? Okay, there are questions like terminological of what you call like the central concentration. And then we have also HST observations for like in the framework of a joint program with Chandra for 5 new intermediate mass black hole hosts. We actually chose the most compact ones that we could resolve from the ground. And those are quite interesting. So this is all coming. Like we already have data for 47 galaxies, I think. So, but if we don't have HST, we still can get away with Magellan, because sometimes you have 0.3 arcsecond seeing, and then you can use it for 4-star observations in the K-band. And it gives you the data quality, I wouldn't say the same as HST, but not much far behind it. And it's also free of dust. So here you see the example like SDSS, pan-stars, and 4-star, and you can clearly see the central compact bulge here. Of course, in the K-band you start having the warm dust, so it's not probably the best, but still it's a reasonable alternative. So we also looked in the archives. We looked in Chandra, in Swift, that is always forgotten as an X-ray, a source of X-ray data, in XMM-Newton, and we don't always look in catalogs because the catalogs are behind the archives by like 5 years. So we, for XMM-Newton, I think it's a little less. For Swift, it's definitely like more than 5. So we actually go in the archives and check for the new data. And then check whether we see sources there or not. The X-ray data analysis is pretty straightforward, and here I'm showing some examples of some of our own observations and some archival observations. The problem with archival data in X-ray is that if it's a serendipitous target, it will be off-axis, where the PSF is awful. So just from the probabilistic point of view, it will be at the edge of the field. So then, you know, we get, but we still get reasonable estimates for luminosities and spectral shapes. And of course, we take into account star formation in the hosts. We take into account the stellar mass, but which is important for intermediate mass black holes because we're getting to the X-ray luminosities, which might be explained by the host galaxy itself, in case it's a strong starburst, for instance. Here, Chandra is better than XMM because it has better spatial resolution. So if you see that the source is really a point source sitting in the center, you're kind of sure that it's, unless it's like a strong nuclear starburst, it should be like an IMBH.
I hate to give you another bit of complication, but if you have an absorbed nucleus, say, in some of these galaxies, which you may have, you also, what we see in the near universe, you're bound to have an extended hard emission component, which will mimic X-ray binary, but a bit higher in
no. If it's an absorbed nucleus, we won't see the broad line in the optical.
Okay.
So
it's not part of your stuff.
So we won't.
Another problem, even with Chandra, if these are small galaxies with a nuclear star cluster, nobody really models the low mass X-ray binary population of the nuclear star cluster, which would probably come.
But here we're still generally we are more afraid of high mass X-ray binaries than low mass X-ray binaries because LMXBs they're much fainter, and we're talking like about 10 to the 40-ish ergs per second. So HMXB is
Old, right?
Yeah. So a nuclear star cluster is like you sometimes have starbursts there, but not very often. Then there's one more thing that is very interesting in the light of time domain surveys, and it's like the variability. Can we call it a poor man's or poor person's X-ray, getting like, you know, in the like gender neutral terms? So there is no answer for this yet. I know that Ricardo thinks that the answer is no. We have the data right now at hand, but we haven't analyzed it yet. So we basically go to time domain surveys, and we have a very sophisticated algorithm on how to take into account the seeing variations, the effects of the host galaxy, which is really non-trivial because, you know, if you're in space, it's fine. If you're in the ground in a like crepey site with seeing varying and, you know, clouds passing by, you really have to be very careful. But at this moment, we're confident that at the SDSS magnitude limit, we can get down to 3% variability. Stay alert, and we'll publish something soon, hopefully. Yeah.
Just to follow up, I think what I meant when we chatted about XMM software RPT, I just think they are they don't talk to each other. They're independent. So
they're independent. That's.
And you try to extrapolate from the population, it doesn't work.
Yeah.
But you need to.
No. I mean, but we cannot say that if we see variability in the optical, there must be an X-ray source.
Yes.
And if there's an X-ray source, there will definitely be a variability in the optical. That's also not true for low mass black holes.
Right.
For quasars, somehow, it's almost always true, but for like massive stuff, but not for low mass. Okay, so far, these are the new X-ray confirmed IMBHs and low mass MBHs. We call them lightweight supermassive black holes, like, you know, the boxing category. These are the ones built between 10 to the 5 and 10 to the 6. So, one slide about the environment. It turns out that, host galaxy and environment. 1/3 of our IMBH hosts are non-dwarfs. So they're hosted by pretty sizable objects, but the bulges are small. So that gives you an important, that raises the importance of optical follow-up, like high-resolution images. Because with ground-based imaging, you cannot really get those galaxies resolved unless you use adaptive optics. And adaptive optics is hard. It has like PSF that is weird and stuff like this. So that's why we ran the HST survey on this. So most galaxies are also in poor environment. That supports the idea of poor merger histories. And those are, but we found a couple of them in clusters. These are the two examples in Coma. There's another one pretty famous in Able 20, I don't remember the telephone number, four-digit telephone number, okay. So here we even see some stuff that might be either an outflow from the black hole, or it can be just the effects of RAM pressure stripping. That's an edge-on low mass lenticular. Anyway, this is a scaling relation compilation from the paper in 2020 by Baldassari, I believe. And that's where we put some of our measurements, like a fraction, because not everything has been analyzed yet, by far. And so we have the outliers here. These are the objects where you have very massive bulges or pseudo-bulges or whatever it is, and they also have pretty high velocity dispersions, and they do have low mass black holes if you estimate them from broad lines. And these are giant low surface brightness galaxies, interestingly. They're also
Igor, the previous version of this plot, you had a guy sitting somewhere here. 10 to the 4th.
Oh, I will.
Yeah, what happened to that guy?
I will show.
You can't fool Ramesh.
This is why I sit here.
You mean on the one that I showed in the my
There was
first?
one guy right in the corner.
Yeah. This I have no idea. This is not my compilation. Okay. This is not my compilation. My compilation is this. Okay. No. Here we actually curated. We looked carefully at every spectrum, whether we had like spurious mass determination. Because if you just run it across Sloan, you might get up crazy stuff sometimes. But these galaxies are still super interesting, and you see there's Malin 1 and Malin 2. For those of you who don't know, these are galaxies that have sizes like radii of 100 kiloparsec, and stellar mass is going to 10 to the 12. And they host small black holes, but they all reside in very poor environments. Okay, now the most important, okay. Yeah, let me just get, because we're running out of time. We have like 8 minutes left, and the most important part has to be shown now, because now we have evidence for both growth mechanisms in place in the local universe. First of all, we found a population of Eddington limited intermediate mass black holes. So basically 1/3 of our sources in both mass tiers, below 10 to the 5 and this lightweight stuff, 10 to the 5 to 10 to the 6, accrete close to or even above the Eddington limit if you use the standard conversion factor from Lx to bolometric luminosity, which is not really very well defined, but still, you know, you cannot get away. Even for some sources, it cannot be below 80% of Eddington, whatever conversion factor you take. Because the X-ray luminosity alone is like 30%, 20%. So, interestingly, we now have HST images for some of them, and they're all sitting in low mass spiral galaxies looking more or less like M33. One of them is not a spiral because it's very close to the cluster core and it's been completely quenched and stripped of gas. There's still a little bit of dust left that you see in HST images. But that's interesting, and we still have no explanation for this. So there's a question on the slide about this. Oh, that's actually very useful if I just grab one of them. Are those selection effects because these are very easy to spot. These are bright in X-ray, so that's why we confirm the objects that are bright, that are luminous, and that's why we have such an excessive amount of high-Eddington active black holes in the sample. Or is it like a physical phenomenon? That's the question. So, and finally, we found one source where we see a double broad line contour persistent for 17 years. And we already observed it like 5 times. Here I'm showing 3 epochs. And the decomposition goes pretty stable for the 2 components. And we infer the masses of 10 to the 6 and 10 to the 5 roughly, or 2 times 10 to the 6 and 2 times 10 to the 5. It's around 1 to 10, 1 to 13. And this is supported by the positions of broad lines in velocity space. So they are split by square, they actually off by square root of the mass ratio on either side with respect to the narrow line component. The host galaxy of this system is a dwarf early type that is in the field, which is already weird, and it has signs of relatively recent minor mergers because it's disturbed. So it has, there's HST image in the archive, and it is, you can fit it with perfectly with 2 Cerseic components which are offset with respect to each other. And there's a nucleus somewhere. So basically the nucleus is coincides with one of them, and the outer envelope is like 300 parsec off, which is like half an effective, 1/3 of the effective radius here. So there is secure identification with both Chandra and XMM. There are 2 epochs in X-ray for this one. We observed it with HST spectroscopically in the UV, and we see some outflow in the UV that we don't see in the optical at like 800 kilometers per second in a form of self-absorption in the C4 and Lyman alpha lines. I'm not showing it here because it's all very preliminary. It's a variable source. And if we look, if we do the math, assuming the typical, like the, we always have problem with the inclination here. So we cannot really solve the orbit. But the orbital period should be around 1,000 years, and it's a sub-parsec binary. So we are waiting for JWST observations that will happen next year. This is an approved target for cycle 2. So that's our evidence that the growth happens with both channels. So this is the key question: which channel is more important? And that relates to the discussion that we already had. And that's actually what I want to ask the audience. So what's your take on this? Because apart from this, I have like 2 more slides, like more like summary.
Well, the answer will depend on redshift, the cosmic time, because the reservoir of gas gets diluted by star formation over cosmic history. And the answer will depend on the host mass, because it's easier to eject gas out of low dwarf galaxies than out of massive galaxies. So the answer is both are viable in different epoch and in different galaxies.
So why do we see then so many Eddington limited sources at low redshift in the local universe? Yeah.
We don't see so many.
I mean, 1/3.
But not the big quasars. The big black holes are not shining.
No, not the big hole. The small black holes. Yeah, the small black holes. Yes.
It's easier to feed them.
It's harder to quench them.
Yeah.
Okay.
I think the answer to your question relates to what I wanted to ask before, that you might, if you select based on the broad line, you are selecting strong ionizing sources compared to everything else being the same, or higher gas density. So you are missing on the other side of the tail, in which you have low velocity dispersion, low black hole masses. So I think eventually DM sigma will look like something like this. That
Yes.
It just becomes a cloud, and we shouldn't use it for
Yes.
mass density.
That's exactly what it is. Because now we have a whole bunch of outliers on both sides.
Yeah.
And this is because when you start working without your initial constraints on galaxy luminosity, that's where you're getting. So, and that's, I already mentioned the giant low surface brightness galaxies. By the way, this is Malin 1, and this is Andromeda galaxy to scale. just to give you an idea of what it is. And it has a black hole that is, I don't know, a few times 10 to the 6. Pretty small.
When the number of outliers is similar to the number of cases on the plot, then there is no law whatsoever.
Yeah, I mean, here we know the outliers. We know these UCDs with massive black holes, which are non-active. Anyway, the future. IMBH observations in the nearest future. So we have E Rosita that produced the sky map, and we're waiting for German data release by the end of the year because it's getting pushed by like 1 week, 1 month, and so on. And like I thought it would be in July, then in September. Now it's at the end of the year.
As soon as the catalog paper is accepted.
Yeah. Anyway, DESI is already working and producing data, and this can substantially increase a sample of optically selected candidates. But there will be also foremost with a dedicated survey on low mass galaxies where I'm participating too, and Franz Bauer is leading this project, and there will be 1.2 million spectra taken with foremost between 2024 and 2029 for candidate low mass AGN, low Eddington AGN. So basically it's trying to scrap the edge of the parameter space in active galaxies. And of course there will be LSST with photometry, and we hope to get the synergy of all these projects. So the question is whether we can detect lightweight SMBH at different redshifts. I think we can, and that's basically that's the end of the scientific part, and I'm leaving with a summary with the main question: whether we can conclude that a population of IMBH in AGN with masses less than 10 to the 5 disfavors massive seeds or not. So what do you think?
You don't know, you don't have the data.
No. We do have the population exists at the low redshift. At low redshift, the fact that at low redshift we see a whole bunch of active IMBHs, does it disfavor massive seeds at high redshift or not?
And by massive, you mean more than 10 to the 5.
Yeah, like massive, like direct collapse.
Yeah, but that could be many different, could be 10 to the 4.
But-
Why do you say that? I mean, stars are up to 100.
Yeah.
So anything beyond that could be called massive seeds.
So you would say everything that is above
It's
100.
non-stellar, yeah. It's like supermassive stars.
Okay, well I would say like maybe not 100, maybe even a bit
1,000,
more, like
well,
150. Yeah.
150
Yeah.
based on this, but-
But still,
Yeah. So
Is there a reason why it needs to be one of the two sitting models?
that's another question. I don't think there's a reason why there cannot be a like dichotomy. So basically, if you assume that it's a star, if it has the time to be on the main sequence or whatever, then it's one thing. But if you consider that everything, it's like a result of a collapse of a gas cloud, but at some point it gets into some nuclear reactions, and at some other point it just doesn't have the time and it just gets directly into the black hole. That's the point.
we reached the time limit.
Yeah, and that's the end of my presentation. And so thank you very much.